My name is Mathias Kemeter, and I'm heading the development team of the Geospatial Processing Engine in SAP HANA, an in-memory data management platform developed by SAP. In my previous role, I've worked as a data scientist at SAP. That's why I'm usually preaching the beauty of data science to GIS experts and vice versa, the beauty of GIS to data scientists. I think in this community, I have to do none of both, which is a pleasure and a premiere for me at the same time. Although I'm with SAP, and despite the fact that my team is developing a product that may be a solution to some of your operational challenges, the core message of this talk is applicable to almost any advanced multi-model data management platform. So don't be scared. I'm an engineer and I'm trying to do my best to not make this a sales pitch. The theme of the day is spatial analysis versus COVID-19. Frankly, I hardly meet that theme. But let's briefly, at least on one slide, talk about COVID-19. So if you have recently read the news, or if you heard Stephanie's talk earlier today, you probably heard that in the UK, 16,000 COVID-19 test results have not been submitted due to an Excel error. Do you know which kind of error that was? In fact, the size limit of the respective Excel sheet has been reached. So was it an Excel error? I tend to say no. The reason was that Excel is not a database, but it was used as such. From that perspective, it was more a data management fail as if it really was an Excel error, right? Do you happen to know what the solution for that error was? The spreadsheet has been split up into two. So I'm not kidding. That was at least the solution that the Telegraph suggested. We're talking about enterprise data management here. So you may imagine that I would have a better solution in mind. Funny story, right? I'm lucky that we don't have that in GIS. Whereas we have shapefiles, right? And shapefiles sometimes can be challenging. And of course, there's also a size limitation. So we have maybe some parallels. I know how emotional that topic is, the Excel topic as well as the shapefile topic. So am I criticizing shapefiles? Am I criticizing Excel? No, don't get me wrong, I'm not doing that. I love Excel, I use shapefiles. It's just a matter of the use case. So when you're doing enterprise data management with mass data, it's probably not the right format or not the right tool to use. Now that we clarified that, let's get back to the presentation. And let me tell you something about multiple data models and the associated silos in a company. So if you look at your company or at any company, you probably have some kind of management silo. You may have a data science department silo. You may have an IT silo. You may have the business department. And last but not least, the GIS department. And don't get me wrong, these are not organizational silos because I think we all got rid of them in the last decade. These are technological silos. Still, every expert department is using its own tooling and there are different solutions. So management tend to use dashboards. Data scientists love their Jupyter notebooks. IT is working on the console. Business in Excel and GIS with the GIS client. And for the GIS department, they may still be that shapefile silo, I don't know. So what if you could run your company on one integrated business platform, which fulfills the specific needs and requirements of each stakeholder? That would be the joy of running on a multi-model platform. So let me tell you about that joy. A multi-model data management platform shall be able to process all different types of data. It should enable experts to use their expert tooling. That's a very important point. So I'm not telling we need one platform and please use the tooling of that platform. I think if you're running on a business technology platform and each department is working on the same data, this platform has to be integrated into the different expert toolings, like into the GIS software or into Excel or Jupyter notebooks or management dashboards. It should be a reliable technological foundation. Of course, that's probably one thing that IT cares very much about. It should transparently combine any kind of data. So if you're working with spatial data and you have transactional data, maybe from your point of sales, you want to transparently get that together and maybe have a management report incorporating both. And it should enable multi-model reporting for non-expert users. And non-expert users, that's not only the management, that's also experts which are not within your area of expertise. So if you're in the GIS department, you're in the data science department, you're regularly in touch with experts from other areas who are ultimately working on the same data and where you need to get a transparent view on that data and you need to provide results in a way that they can understand that. So what does multi-model mean to SAP? SAP is offering SAP HANA Cloud as an integrated multi-model data management platform. It brings together support for graph, spatial, relational data, semi-structured data, topped with embedded machine learning and advanced text search capabilities. So that's all that you can do in the data management platform. The multi-model engines in SAP HANA benefit from the cloud and computing qualities of the underlying HANA platform, which is, for example, in-memory computing and enterprise integration. For more detailed information on that one, just visit saphanajourney.com. Since this conference is all about spatial data science, in the following I will touch upon 2 examples on how to combine spatial data with embedded machine learning on a data management level. The first example is about making sense out of vehicle trajectories. Trajectories are usually something that is hard to handle by standard machine learning algorithms. To predict the travel time and destination for taxi rides in the city of Porto, I used an XGBoost regression and clustering model, which is available on SAP HANA. It is based on historical taxi trajectories of the years 2013 and 2014, which you essentially can download from Kaggle. Spatial data preparation and machine learning have been done 100% on the data management level, and the orchestration and visualization happened via SAP HANA's Python integration. So as you can see on the pictures here, for the visualization, I used Kepler GL in the Jupyter Notebook directly. So if you now look at the results here, you see on the left-hand side, maybe here at the top, you see the actual prediction. So we're trying to predict the duration of a taxi trip at 5 o'clock in the morning. From one area to the other area. So it's all based actually on an hexagonal grid that I laid over the city. And we're predicting here the same trip at 5 o'clock in the evening. And you can see that there seems to be some rush hour pattern. So the very same trip in the morning is quicker than the trip in the evening. On top of just predicting the travel time, I also predicted the target destination, which might be interesting if you're doing taxi operations, for example. You would want to know which taxi is when in which area. So if you take the very same trip, which is starting here in that green cell, and on the left-hand side, you see the trip starting westwards, you see the probability distribution of the destination over the city. So there's quite some probability that the trip is going to the seaside. There's a rather high probability that the trip is going to the airport out here. And the actual prediction would be the cell here in the inner city. I mean, generally, you see that the probability that the trip is going to the center of the city is rather high. That's just some general correlation that we see in the data. On the right-hand side, you see the same trip at another time of the day and heading towards another direction. So for the direction, I have to say that I incorporated the first, I think, 5 GPS coordinates or something to just get a grasp of in which direction that taxi is heading. And here you see that the probability that the trip is going to the seaside significantly decreased, whereas the probability that the trip is going to the northeast over here increased significantly. The actual prediction would be the cell over here. A detailed blog comprising the full Jupyter Notebook can be found with that link here. So bit.ly/SAP HANA Spatial. This is actually where I just put together some material and some blogs which are behind that very brief presentation here, if you're interested in more details. So now everyone can preach that adding geospatial features to a machine learning model results in a benefit. But I'm a mathematician, and thus I had the noble goal to find an example where I could really quantify or measure the impact of the geospatial dimension to a machine learning model. The example I found was a housing price prediction, which I could easily do with and without location information, and in the end, compare the models by numbers. The model without location information would only incorporate non-spatial features, such as the size of the land in the house, the number of the rooms, the number of the car parks, and so on. The model with location information would, in addition, have the latitude and longitude information, as well as any features that I'm able to construct out of this information. But in the base data, it would only be latitude and longitude. And finally, I was hoping to get a proof for what I've preached before. Good. The data set I found on Kaggle comprised more than 30,000 housing sales for the city of Melbourne. What I did first, I actually augmented the data with OpenStreetMap point of interest data to just get a better understanding of the neighborhoods. For that points of interest, I measured the proximity and the density of points of interest around the house listings. So I categorized points of interest. For example, I said bars is of type entertainment, so bars, restaurants, anything related to that is an entertainment point of interest. And so I measured for each housing what's the closest entertainment point of interest, and what's the density of entertainment points of interest around that house. The next thing, I introduced the region proxy by using in-database k-means clustering and computation of Voronoi cells. This proxy would give my model a grasp of the different parts of the city. So as you know, you typically get expensive or inexpensive suburbs or neighborhoods where simply the name justifies a certain price. Since I don't have it in the data, or I excluded it before for my artificial example, I wanted to somehow have a data-driven way to infer that region proxy, let's say. Finally, I added areas of interest like the Bay and the Central Business District. Overall, I computed more than 20 geospatial features in addition to the non-spatial features. And what was the result? I could actually prove that the model incorporating spatial features is more precise and, even better, significantly more robust than the model without spatial features. So if you look at the error ratio, you would see that for the mean, it's the last one, the mean absolute deviation between train and test. From my point of view, that's the most interesting one, because we expected that the model would get more precise, right? So if you look at the robustness, then actually the deviation for the non-geo model is 25%, where the model on the test data set is worse than the model on the training data set. For the geo model, or for the spatial model, the deviation is just 5%, whereas the test error is actually smaller than the error on the training data set. So you could even argue that this is zero. As a fun fact, which I found out, the non-spatial model identified the building year of the house as most impactful feature. According to the model, older houses tend to be more expensive. You can see that the impact of the geospatial dimension was so strong for that example that it was even present in the non-spatial model, because where do old houses usually exist? Right, in the center of the city. So my suspicion is that this was simply a proxy for the distance to the center. To get an understanding of the expensive and less expensive areas of Melbourne, I predicted the price of a reference house while moving it virtually all over the city. My reference house had 600 square meter land size, 160 square meter building area, and has been built in 1965. Like all the other attributes were around average values which I found in the data set. I applied an hexagonal binning and predicted the price of the house for the centroid of each cluster cell. So as all the non-spatial features were fixed, the only difference is actually the location. And you can see in the picture here clearly that the housing prices increase in the center and at the Bay, which is not that surprising. The price of the very same house varied between 330,000 Australian dollar and 2.5 million Australian dollar, depending only on the location and nothing else. I hope that this example kept you entertained, but why am I telling you this? The essence of those examples from my point of view is that the analytical computation can be done 100% on the data management level, which means the result can easily be made accessible to any application you may be running on top of that platform. This may be your Esri landscape, your SAP applications, your custom applications, your open source GIS, or your management dashboards. They can all access the same model. They can all do the same predictions by simply executing database logic. And what you see on the picture here, this is how our customers typically leverage their spatial and multimodal data in SAP HANA. So as I mentioned, you have the Esri landscape connecting to the Geo database. We have a plugin for GeoServer where you can connect any custom application or other GIS software. And of course, the SAP software like SAP Analytics Cloud ERP systems connect to SAP HANA and connect to the underlying data pool. Spatial data is just one example in the wide multimodal world. As I mentioned in the very beginning, there's a variety of domain-specific data and data models, each domain having a different view on the data and having different tooling. This talk is about building applications. So who is building applications? One might naively think the application developer. This is not true anymore, and actually it was never true. It just gets more relevant since applications today are extensively more data-driven as opposed to past decades. Applications are built by expert teams, ingesting, processing, and visualizing different kinds of data. And yes, there's an application developer developing the technical framework. In essence, what I want to say with that talk, your data is a treasure, and so is your business logic. You should keep it both as a treasure and democratize it by breaking down the technology silos that you may still have. And data and business logic needs to be kept accessible for each persona and application in the company. This is about building applications as a team. And this is how you really boost your applications. And of course, in-memory processing performance with enterprise integration is also beneficial. With that being said, I would like to thank you for your attention, and I'm open for any questions in the chat. Let me quickly check. So, the first question that I see, how does SAP HANA Spatial perform on massive vector data sets? E.g., a billion adjoint polygons that can be edited, but the whole contraption needs to maintain topological consistency and neighborhood relations. I am biased, so I'm the engineer. I tend to say it performs good, but of course, the best thing is you should have a POC actually on that data, because it's highly dependent on the data. It's highly dependent on the workload that you have on that data. What I can say is that compared to other geodatabases that you may know, at least for HANA, the in-memory and column-oriented concept is something which gives us extensive boost. The other fact is that we're actually, from a geospatial processing perspective, we're developing our own C++ code, our own geospatial library tailored to SAP HANA, so we're not plugging in anything else. That means that all the processing that we have is really optimized for HANA. Good. How does SAP HANA implement spatial indexes? Actually, so what we have per default is an approx box index, and if you have I'm sorry, I always mix that up. I think it's low selectivity queries. So no, it's actually from database perspective, I think it's high. Is it low? So you're selecting a little number of points from a large amount of points. You can actually use the R-tree index or the Hilbert curve, but that's optional. So you have to define that at the point where you actually create the column. What kind of spatial joints are supported? So SAP HANA as such is OGC compliant. That means you have all the spatial predicates that you would expect and can use them for spatial joints. I hope that was the question. Does it support 9 intersection model? That we maybe need to clarify offline, because I don't know what 9 intersection model is. What are SAP HANA spatial capabilities on raster data? That's an easy one, close to 0. So we're talking about processing of vector data in the database itself. For example, Postgres uses GIST R-trees. Yes, correct. Okay, OGC compliant, awesome. Yes, so we're OGC member, and actually we have, meanwhile, I'm not counting, but more than 100 spatial functions, which are OGC compliant, and we deliver, for example, in database clustering. Like I mentioned, we have k-means, grid clustering, hexagon, Voronoi cells. Did I mention dbScan, which is actually beyond the OGC standard.
Great, thank you very much, Matthias. If anybody would like to ask Matthias any more questions, I think you can do so on the SAP booth. Matthias will be there and available to talk to you. So thank you so much for taking the time to prepare for today, and see you soon, Matthias.
Thank you very much, and have a good day.